Welcome back, students. In the last lecture, we derived expressions for the Gibbs free energy and the Helmholtz free energy, and we determined the spontaneity condition that the change in Gibbs free energy is negative for spontaneous processes. Today, we're going to apply delta G to a simple process that is the mixing of the substances, namely ideal gases. The goals for today are going to be to define and apply the chemical potential. We'll use this idea of chemical potential to derive the Gibbs free energy for mixing. And then we're going to use this chemical potential to actually calculate the Gibbs free energy of mixing. We expect that the Gibbs free energy for the mixing of gases is negative, since gases obviously mix. They expand to fill their containers regardless of the other gas molecules that are in there. After this, we are going to go on to apply this to chemical reactions, and we'll do that next time looking at the equilibrium constant. So today we'll start by considering the total differential of the Gibbs free energy. So what we're going to do is consider what goes into the Gibbs free energy. We saw last time that the Gibbs free energy is a function of temperature and pressure. However, the Gibbs free energy in a reaction is also a function of the number of moles of substances in the reaction or the process. In other words, our Gibbs free energy is not only a two-dimensional function, but it is an n-dimensional function where n is the total number of variables that goes into it. So if we have a two-component system, we have Tp and then the number of moles of substance 1 and the number of moles of substance 2. Depending on the complexity of the reaction, this can go on and on and on. So if we want to calculate how the Gibbs free energy changes, we can't just consider how the Gibbs free energy is changing as a function of temperature and pressure now, but we also must consider how the Gibbs free energy is changing as a function of the number of moles of substance in the reaction. And so we can do that in the exact same way that we have been doing it, although it is a little bit more complicated looking because we have more terms. So we can write that dG, which we will integrate into delta G, is equal to the rate of change of the Gibbs free energy with respect to temperature at constant pressure and the moles of all our substances. Then we multiply that by the extent of the temperature change. Then we move on and take the rate of change of the free energy with respect to pressure at constant temperature and constant all of our substances, multiply that by the pressure change. And then we go take the partial derivative of the Gibbs free energy with respect to substance 1 at constant temperature, pressure, and every other substance, multiply that by the change of substance 1, and so on. And we have this relationship here. What we'll note is that this term here, this dg dn1 at constant Tp and every other n, appears relatively often, and it's so often that we give it its own unique symbol, and that is the chemical potential. So we use a mu sub I. Here I is whatever the species is, so we could have the chemical potential of hydrogen gas or liquid water or anything like that. This chemical potential is an important concept. So the meaning behind the chemical potential, you can kind of see it here from this derivative. It is the Gibbs free energy per mole of substance. So it is the molar Gibbs free energy for a particular substance. This chemical potential is also a form of potential energy. So just like objects move from higher to lower gravitational potential energy, and what I mean by that is objects fall, their gravitational potential energy is their mass times the gravitational force constant times the height. So at higher heights, they have higher potential, they fall to lower potentials. Chemicals also move from higher to lower chemical potential. And what that means is, again, something that we're very familiar with. They move from high concentrations to low concentration. And while that is obvious, here when we're talking about this in terms of free energy, and remember free energy is related to work, we can make a connection that it actually takes energy in the form of work to move a molecule against a concentration gradient. So these sorts of ideas are very important for biochemistry. So if we think about a cell is very nutrient rich compared to the environment. There's a lot more things like glucose inside of cells and outside of cells. So if a cell wants to take glucose, it has to take glucose from a relatively low concentration environment inside of itself with a relatively high concentration environment. And to do that, that cell must expend energy in the form of ATP. In the opposite way, cells also generate ATP. If you remember back to our biochemistry classes, cells generate ATP in the electron transport chain, and there is a proton gradient. Now, what happens in the mitochondria of cells is that there are more protons on one side of this mitochondrial membrane than the other, and that creates a concentration gradient. The enzyme ATP synthase allows the hydrogens to fall through, going from high concentration to low concentration. When this happens, this is basically like a water wheel. When a water falls from a high level to a low level, we can put a paddle in there and then crank that paddle and actually get energy from it. ATP synthase works in the exact same way. It harvests work that comes from a result of chemical potential, and it uses that to actually form molecules of ATP. So this idea of chemical potential is going to be an important one for us, and it also is important in a lot of various aspects of chemistry, namely biochemistry. So with that aside done, we're going to go back to considering the mixing of gases. What we're going to do is substitute in this chemical potential here. So we can say that dG is equal to these first two terms that are the same, and then it's simply the sum of all of our other terms, where we replaced our complex partial derivative here with the simple mu. Remember, they're the same thing. What we'll then do is note that often our chemical processes are happening at constant temperature and constant pressure. So for example, if I took a balloon and I popped the balloon, the helium, if it was a helium balloon, inside that balloon would mix with the air at constant temperature and pressure. So pressure and temperature are constant, dT and dP are 0, and these two first terms go away. And we can simply describe the mixing of gases by the change in chemical potential of the substances that are mixing times the extent of the change. And we can go ahead and integrate this here to remove the D's. And what we get is that the Gibbs free energy of a gas mixture is equal to the chemical potential times the moles of that gas in the mixture. And we've been talking about how substances flow from high to low chemical potential. How are we actually going to apply this idea to mixtures and describe how gases mix? Let's consider a system where there are two gases separated by a barrier. Now, this is an interesting example here where we have a semi-permeable membrane. This might be counterintuitive, but it turns out that gases expand to fill their container. So in this case, hydrogen, if we had hydrogen on one side and argon on the other side, the hydrogen, if it would go through this membrane where the argon couldn't, would go through this membrane and actually equilibrate with this membrane regardless of what this argon is doing. And that's a little bit of an interesting idea to kind of wrap our minds around. So the hydrogen would spread out to fill its container. For a little bit of an easier example, let's think about having a whole bunch of different gases separated by barriers, and we can go ahead and remove these barriers. What's going to happen? Well, we have a pretty good idea of what is going to happen. The helium, neon, argon, and xenon in this case will all spread out to fill their container. So if we remove this barrier, the xenon gas is not just going to stay up here where it used to be sequestered. It's going to spread out over the whole container, and so will argon, neon, and helium. So how can we describe this mathematically? Well, if the mixing is happening spontaneously, which of course it does, that means that delta G for this process must be equal to 0. So how can we actually calculate the delta G of this process? And to do so, we're going to go to the board and go through a little bit of the theory behind this. What is going to happen to these molecules as they mix? Well, the way that we normally describe gas molecules, and you may be familiar with this from considering hemoglobin in biochemistry, is that we refer to the amount of gases usually by their partial pressure. And as we mix these gases, so here xenon has a certain pressure. As we mix it, it's going to mix in with all of these other gases, and the total pressure of the system will be simply equal to the partial pressure of all these individual gases, and then add those together. So we need to figure out how the chemical potential changes with respect to pressure. The chemical potential that we would calculate before, this mu, is at assuming standard temperatures and pressure. Lucky for us, we already have an equation that tells us how we calculate delta G's at different pressures. And remember, the chemical potential is simply a molar Gibbs free energy. So what we're going to do is take advantage of the equation that we derived in the last lecture. So we had delta G at a final pressure is equal to delta G at an initial pressure plus nRT natural log of P final over P initial. Now, since our chemical potential is simply a molar Gibbs free energy, if we divide this whole thing by N, we would have that mu, the chemical potential, at some final pressure is equal to mu at some initial pressure, and then plus RT natural log of P final over P initial, because mu is a molar Gibbs free energy. So we simply divide by N. Now, what we'll note is that for this purpose, our initial pressure is going to be standard temperatures and pressure. So if we choose our initial pressure to be 1 bar, what happens to this? Well, what we're going to do is instead of writing P initial, we'll write P degree, where that degree is talking about the standard conditions. So here we would have the chemical potential at some final pressure P is equal to the chemical potential at the standard pressure P, and we could denote that by mu degree, the standard pressure, and then plus RT natural log of P over P degree. Now, what is the pressure of our substances in our mixture? Well, the pressure of our substance in the mixture is simply the total pressure times the mole fraction of that substance. So if we had, and what I'm saying here is that if we had a system with a certain pressure, all of the pressures of those individual gases added together get the total pressure. So we can represent this in the following way. We can say that our chemical potential is equal to the standard chemical potential plus RT natural log. And here we'll write the pressure of our substance times the mole fraction of our substance. So what we actually need to do is say PA XA. This is component A in the mixture. And we can go ahead and put a mu A here as well, if this is what we're talking about. So for substance A in a mixture, the chemical potential is equal to this term here. Now we're going to split this up one more time. So I'll write it in a new equation. We'll have our chemical potential of substance A at some pressure is equal to the standard chemical potential of substance A plus RT natural log PA over P naught plus RT natural log of XA. Now, all I've done here is pull out that XA from the natural logarithm. Why have I done this? I've done this because here we can see there are 3 terms that all have a clear definition. So this term here is the chemical potential of substance A at standard temperature and pressure. This term is a correction to say that we are not at standard pressure, but we are at a pressure of PA, whatever PA is. And if we were at standard pressure, so if PA was equal to 1 bar, that would give us the natural log of 1, which is 0. So this is a correction term that says, okay, if we're not at our actual pressure, we're at a different pressure. How do we correct that? Which is the same as we showed up here. Now, what's this term? This is a term that's a correction representing the fact that we are not at pure A. We're in a mixture. We have a mole fraction that's not 1. Again, consider what would happen if our mole fraction of A was 1, then we have the natural log of 1, and that would be 0 again. So if we were at a pure A at 1 bar, this would just be the standard chemical potential. However, if we're in a mixture and we're not at pure A and we're not at 1 bar, these 2 terms come into play. What we can do, and what we'll often do, is group these 2 terms here together, because these are reflecting species A as a pure substance. So we can say that this is equal to mu, and we can write a little pure here to remind us that this is talking about having a pure substance at some different pressure, plus a term that accounts for the change in concentration. So here we have a nice expression for what's happening to our chemical potential as our substances mix. Now, in the slides, we had an example with 4 gases, and in theory, we could go through and do this math with 4 gases. However, it's a little bit easier to do it with only 2 gases. So let's go ahead and consider what would happen if we mixed 2 gases. We have gas A and we have gas B. What would happen? Well, we'd want to calculate the delta G of mixing. And that is simply equal to the final Gibbs free energy minus the initial Gibbs free energy. The Gibbs free energy is related to the chemical potential. So we can say that the Gibbs free energy is equal to the number of moles of gas in the system times the final chemical potential minus the initial chemical potential. So how can we go about figuring out what this is? Let's calculate first the initial Gibbs free energy, and then we'll calculate the final Gibbs free energy. So the initial Gibbs free energy is the following. It's equal to N times the chemical potential of the initial state. So if we have two gases prior to mixing, they are pure, and they are their Gibbs free energy is equal to Na, the number of moles of substance A, times mu A, the chemical potential of A, at whatever temperature and pressure it's at. And then we also have Nb times the chemical potential of B at whatever temperature and pressure B is at. Now, when the mixing occurs, so after the mixing happens, what's the final Gibbs free energy? Now we have mixing. So now we have to consider this expression as well. So our final Gibbs free energy is Na, and then mu A Tp plus RT natural log of XA. And then we have plus Nb mu B at temperature and pressure, plus RT natural log of XB, the mole fraction of B. And this is our final Gibbs free energy. If we take the difference of these, the delta G, we simply subtract the initial Gibbs energy from the final Gibbs energy. And you'll note that this term would cancel out with this term, and this term would cancel out with this term. So the delta G of mixing, how the Gibbs free energy changes of mixing, only takes into account these mixing terms. And so what that would be is RT natural log of XA, Na, RT natural log of XA, plus NB, RT natural log of XB. And we can put this in a sum if we have more than two components, and it would be the sum over all of our components of Ni RT natural log of Xi. And to make this a little bit nicer, we can actually have a relationship here between the mole fraction and the number of moles. So Ni, the number of moles of component A, is simply equal to N times Xi, the mole fraction of component A. So we can also write this as nRT times the sum of Xi natural log of Xi. And this is an expression that talks about the delta G of mixing for gases. Now, what can we note for this? What's the mole fraction? Well, the mole fraction is necessarily a fraction. And so that means we're taking the natural logarithm of a number that's less than 1, and that is always negative. So delta G for ideal gases is always negative, and this explains to us why gases always mix. In a different way, we can see that with the entropy. So the entropy of mixing we can calculate using our thermodynamic relationships. We saw previously that the change in entropy for mixing is equal to the negative partial derivative of the Gibbs free energy with respect to temperature at constant pressure. So that is simply the temperature derivative of this equation here, which is negative nR times the sum of Xi natural log of Xi. So just like the Gibbs free energy is always negative, the entropy of mixing is always positive. It's always better for gases to expand to fill their container. We can also say an interesting thing here if we try to calculate the enthalpy of mixing. So using the relationship delta G is equal to delta H minus T delta S, we can come up with that the delta H of mixing is equal to the delta G of mixing plus T delta S of mixing. And what we'll note is that what we did to get between delta G of mixing and delta S of mixing is make it negative and remove the T. So if we plug in these numbers here, we get that delta G of mixing is nRT times the sum of X natural log of X. And the entropy of mixing is T plus minus nR times the sum of X natural log of X. In other words, the enthalpy of mixing is 0. Now, think back to general chemistry. What is enthalpy. Enthalpy is similar to internal energy. It kind of talks about the energy that the molecules have. So what this shows us is that for gases, mixing gases together does not have any net interaction with gases. They don't interact with each other, and they don't really change how they function just because we have more gases in the system. And this is why all gases mix. Now, this is not true for something like liquids. So the difference between solids and liquids and gases is that solids and liquids necessarily interact with each other. So gas molecules approximately don't. We can model them as ideal that they don't interact with each other. We can't do that for solids and liquids. So solids and liquids have interactions, and in some cases, especially for liquids, they have very negative interactions, or so the enthalpy of mixing would be very positive. And that means that these molecules wouldn't like to, say, touch each other, and that could actually cause the overall Gibbs free energy for mixing to be positive. So this explains why some liquids don't mix, because they have unfavorable interactions that overwhelms the spontaneity from the entropy in terms of mixing. If we use our simple two-component reaction, we can note that there's a relationship between XA and XB. So if we know XA, the mole fraction of the substance A in solution, or in the gas phase, the mole fraction of B is simply 1 minus A. So we can say that XA is 1 minus XB, or XB is 1 minus XA. And there, because we only have two components, so if A is 0.6, then B has to be 0.4. That's how the mole fraction works. And so we can say then, using our expression over here, that our Gibbs free energy of mixing is simply nRT times x natural log of x, where here x is equal to XA. And then the XB component is x minus 1 natural log of x minus 1. And this is a nice simple expression for our two-component system. So we'll go into the slides and look at these graphs and see what the most favorable value would be. Like you probably expect, the most favorable value is 0.5. That represents complete mixing. So if we have two substances, the lowest Gibbs free energy comes from having all of these substances equally spread out. And the same is true for the entropy of mixing. All that changes is the sign, and then the magnitude here, just removing the temperature. So here we can see that gases will spontaneously go until they're equally mixed. And once they're equally mixed, there's no more equal for them to go. There's no more driving force for mixing. And so that is all we'll go into for today. We'll pick up next time for a bit longer of a lecture. We're going to go through the remaining half of chapter 6, which covers chemical equilibrium.